Okay, so last time we were looking at what's called the Foldy-Woutersen transformation. Uh, so we had just completed the study of hydrogen atom problem in the using the Dirac equation, and we wanted to basically take non-relativistic limit and write down terms uh, coming from the Dirac equation, which are systematic relativistic corrections to the non-relativistic problem. So the first thing that we did was to look at the free particle problem, and that was kind of a relatively easy exercise. But nevertheless, we'll just go through it once again. Uh, so the free particle Dirac Hamiltonian given by h is equal to c times alpha dot p plus beta mc squared. And the idea of Foldy-Woutersen transformation is to write down the Hamiltonian in a form uh, in which the entire Hamiltonian is in a diagonalized state. Okay, and of course, for free particle, it is possible to do, but for the interacting system, it may not be as easy to do. Okay, in fact, in this particular case, also what you find is the canonical basis of alpha and beta matrices that the term beta mc squared is already diagonal because beta matrix was diagonal, and it is alpha dot p term which is the one which has off diagonal entries. And the idea of Foldy-Woutersen transformation is to find a similarity transformation which will convert this Hamiltonian into a new Hamiltonian in which everything would be diagonal. Okay. Now, uh, so that is the idea. Basically, you want to get rid of this term. Of course, when you say when you want to get rid of it, you don't want to get rid of it by just setting p to 0. That would, of course, naturally give you a diagonal Hamiltonian, but that's nothing interesting. Okay, but what we want to find is a similarity transformation, and that similarity transformation turns out to be exponential of beta times alpha dot p times some angle theta, and that angle theta, of course, depends on various other quantities. In this particular case, on p times c and mc squared p's. And in fact, if you take tan 2 theta angle to be mod p upon mc, then this is the transformation which would give you h prime uh, in a diagonal form. Okay, and it is of course multiplied by beta, but which is a diagonal matrix, and beta has two positive eigenvalues and two negative eigenvalues, and therefore you clearly see that h prime has both positive and negative eigenvalues. The kind of problem that we encountered in Klein-Gordon equation resurfaces here again. Okay, but what we are interested in is not really to do this, because this fact was noticed even while doing Dirac, uh, while solving the Dirac equation, even free particle Dirac equation, even without doing the diagonalization or in this particular form, by doing the similarity transformation. Of course, you can, when you solve the problem, you of course diagonalize Hamiltonian anyway. What we want to do actually is to utilize this technique to bring the hydrogen atom problem in a diagonalized form. And in this case, of course, because of the interaction terms in the hydrogen atom, it's like like the Coulomb potential term. Exact diagonalization is not possible, but we can do it in a systematic way. Okay. Now, of course, the procedure is technical, and I would kind of like to go a bit slow uh, through the steps. In case you feel that I'm still going fast, you please let me know. Of course, not all steps are given here, so computing intermediate steps would be part of the home assignment, which I'll send out in a day or two. Okay, but the in-between steps of kind of completing this computation are not very complicated. You just have to sit down and kind of systematically compute the relevant commutators. Okay, so it is not like, you know, very complicated computation, but it's a meticulous computation. Okay, So here's the Hamiltonian that we have. We have beta MC squared piece, and then you have C times alpha dot P minus E by C times A vector, and the Coulomb potential. Okay. Of course, what we will really look at uh, is a problem where uh, we would want to kind of diagonalize this Hamiltonian as much as possible. Okay, so it's not like entire diagonalization would be done. And in this particular case, the first two terms are already diagonal because this is a beta matrix, which is 1 minus 1 diagonally, whereas this is proportional to identity matrix, which is of course diagonal. Okay, it is the alpha matrix, which is the kind of off diagonal part of the Hamiltonian, and we want to get this piece back into a diagonal form as much as possible. Okay, so we'll follow the same method. We say that we look at psi prime, which is e to the I times s times psi, and uh, just carry out the process. Okay, so Hamiltonian, of course, is same as I del t acting on the wave function. So I just invert this. I del t on psi is same as exponential minus I s times psi prime. Uh, I del t acting on that. Okay, but I del t is same as the Hamiltonian. So therefore, this expression is same as h psi. Okay. Now look at the left hand side. You can either take the derivative on psi prime, which is the first term, e to the minus I is I del t on psi prime, or I del t act on e to the minus I s, which is the second term. Okay. So now you can just rearrange this entire piece. You pull I del psi prime by del t on the left hand side, and you multiply by e to the is, so that e to the minus is is gotten rid of. Okay. So if you do that, then you can push this second term to the left of this equation. Okay, which in the next step actually looks like it is a term on the right of the equation, but it's the same stuff. You have multiplied the entire stuff by e to the is, so you get e to the is h times e to the minus is, because psi is e to the minus is times psi prime. Okay, so psi prime is pulled out, and this term has a e to the is times minus I del t on e to the minus is. Okay, so that is the expression. So if you look at it a little carefully, you could pull e to the minus is out. Okay, and therefore new Hamiltonian h prime is just a similarity transformation e to the is of h minus I del t times e to the minus is. Okay, so that is the new Hamiltonian. Okay, so what we want to do is to claim that h prime is a diagonal Hamiltonian, whereas h is the Hamiltonian which we have written down up here. Okay, fine. Now, as I said, that it is not very easy to diagonalize it right away. So what we will do is we will claim that we are choosing S in kind of systematic fashion. We write down S equal to S1 plus S2 plus S3 kind of stuff, and we figure out what S1 is, use that, diagonalize parts of it, then select S2 in a convenient fashion so that diagonal terms do not become off diagonal and so on. Okay, fine. Now, our intuition with the first computation was that if you have an off diagonal piece which is alpha dot p, then the transformation that you require is same alpha dot p but multiplied by beta. Okay, so let's do that first. Okay, so let's consider that. Okay, so okay, maybe we first kind of just do this step and then we talk about it. Okay, so uh, so the idea, as I said, was to choose S in such a way that the off diagonal part of H prime is minimized, simply because you can't do exact diagonalization. Okay, now uh, here is a Baker-Campbell-Hausdorff formula once again. This formula is going to come in different places. Uh, uh, so, uh, so if O is an operator, and if you do a transformation like this, I'm putting lambda up here. We don't have lambda in our transformation here. E to the is operator, e to the minus is. But I'm putting lambda just as a power counting parameter, so that when you do an expansion, you can just write that as summation n going from 0 to infinity I lambda to the n upon n factorial. And that tells you that you will have n such S's having a commutator with O. Okay, so it's a kind of a nested commutator, that S commutator with S commutator with S commutator dot 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 of all the way up to commutator of S with O. Okay. Now, of course, when you want to do this computation for this type of expression, then of course you are just going to set lambda equals 1, and that would give us our answer. Okay. But it is a good idea to keep lambda so that it is easy to keep counting of the powers of S's that are occurring when you collect terms, when you expand an expression like this. Okay, fine. So what we are going to do is to use this formula where to write down H prime, where O will be our H minus I del T, and this entire expression would be interpreted as H prime. Okay, and we are going to kind of compute this in powers of V by C. That is why one calls it non-relativistic limit. And we will kind of work out terms only up to this order. Okay, I mean, if anybody has patience, can go further down. But like as far as whatever we want to do in this course, these terms up to this order are good enough. Okay, fine. Uh, so yeah, so I think there's a typo. I should have said this is H minus minus I del T. That's what I should have written here. So as I said, as in our case, it should have been the operator is H minus I del T, and we need to find S such that the that we can diagonalize several of these terms in this Baker-Campbell-Hausdorff formula. Okay, so all I have done now is basically substituted O to be not H, it's a typo, but H minus I del T here, and just wrote down a few terms in that series. Okay, so there are dot dot dot. These ellipses we are not going to look at. Okay, so this is a set of terms that we are going to look at. Fine. Okay. Now notice one thing, that when while writing this term, I have written down the leading term, which is H. That is kind of easy because when n is equal to 0, then there is this is 0 factor is 1. This to the 0th power is 1, and there's a 0 commutators of O with S, which just means it is O, right? So that is this term. The next term would be lambda to the first power, which will have one commutator, which is this term, and so on. Okay, but you can see that like I write down H commutator of S with H, commutator of S with commutator of S with H, all the way. But when I write down this term, I just write down beta MC squared piece. And the reason for doing that is because I want to keep terms which are only up to order V by C to the 4. And if I write down alpha dot P piece here, alpha dot P piece is V by C down compared to beta MC squared in the non-relativistic limit. And already these S's would have alpha dot P pieces at the leading order itself. Remember, as I said, we are going to follow this intuition that if you have alpha dot P, then your S contains alpha dot P. So this factor is already kind of, this is like M times V in some sense. So it is V by C down compared to beta MC squared piece. So therefore, if I had kept, I could have kept that term, but effectively, if I'm just looking at terms up to this order, the fourth commutator piece would be just commutator with beta MC squared. Okay. The remaining terms, S dot, commutator of S with S dot, and so on, these pieces are the ones which come from minus I del T acting on the similarity transformation. So that is the reason why this is not correct. Okay, fine. So let's consider our S to be S1. As I said, we are going to take them in steps. Okay, and we are going to follow the same intuition that we had from the free particle case. That is that the operator is beta times some operator O, which is proportional to alpha dot P. Okay, it was alpha dot P for free particle, but we have an interacting Hamiltonian which contains not alpha dot p, but alpha dot p minus e by c times a. Okay, so we just choose this entire piece, multiply by beta, and treat that as our similarity transformation uh, matrix. Okay, good.
So,
Yes.
do we have a minus I del by del t like extra in the above expression? Like S dot comes from the n equals 1 term.
S dot comes from.
From the n
Oh,
equals 1 term, the
yeah,
S comma iota del by del t will give this minus S dot,
yeah,
and iota will get cancelled.
yeah.
And so from the 0 term, n equals 0 term, will we get some del by del t?
Uh,
Like the way we got H. H we
oh, yeah,
got,
yeah, yeah, yeah. That is right. You have a del by del t term sitting around, but that is not part of the Hamiltonian. No?
yeah.
H H prime on psi prime is equal to I del by del t psi prime, right?
Yeah, okay.
So that I del by del t piece is there, but that is not H prime. It is on the right hand side of the equation. So that's why it is not written in the H prime expression. But yeah, it is there when you expand the expression. Okay.
Yeah.
Yeah. Good. So now what we'll do is we will take this following our free particle intuition and substitute S1 as beta times O upon 2mc square, which is minus I factor, and plug it into these commutators. Okay. So now I'm not going to work these commutators out, but I'll soon send out a home assignment in which you'll have to do this computation. Okay. This itself would be a home assignment actually. If you look at it, a lot of computations need to be done. They're all straightforward, but it's not like you just stare at it and you know the answer. Okay, so that's not what happens really. Okay, so just give me a second. Let me split screen so that you can see the expressions. Yeah, fine. Okay, so here's a Hamiltonian at the bottom screen, and we want to choose S as up to minus I by 2 mc squared piece. It is beta times O. Okay, and now you want to compute this commutator of beta times O with Hamiltonian. Okay, and you can check that the first term is the one which is responsible for you to get this expression. Okay, the second term is the commutator here. It's kind of trivial. Okay, the third term, okay, which is itself is a term which is O, right? O commutator with beta times O, you can check that you will get an expression like this. Okay, so that is the first commutator. Now we want to take this expression now and take its commutator with beta times O. Okay, that is this term, right? Because S is up to some these factors like minus I by 2 mc squared. This is beta times O with this object. Okay, factors of I and R we can take care of, but effectively this. Okay, so that commutator gives you terms of this type. Okay, now notice one thing, that when you look at this commutator of S with H, then you have a term which is proportional to O here. Okay, then you have a term which is beta times commutator of O with E phi, and then you have a term which is beta times O squared. Okay, now notice that the term which is beta times O squared is let me just go back. O is just alpha dot p. There is no additional factor. Okay, alpha dot, let's call it pi. Okay, so if you kind of look at this term carefully, then alpha dot pi squared, okay, is the expression which is diagonal because alpha squares to identity, right? So therefore, this expression is actually diagonal. Okay. On the other hand, the term proportional to O is not diagonal because it contains alpha dot p. Similarly, there is a term here which is not yet diagonal. Okay. If you look at the double commutator, then you get a term which is beta times O squared like that again, and that is also diagonal. Okay. This is a term again which contains two alphas. Okay. Times identity matrix piece, and therefore this is also diagonal. Okay. But there is a term which is proportional to O cube, which is not diagonal. Okay. So what you find is that you, by doing this transformation with two commutators, you have got some terms which are diagonal, but some terms continue to remain off diagonal. Okay. If you continue doing this computation, okay, or this should have been comma. If you continue doing this computation, a triple commutator gives you a term like this. Okay. In that beta O to the 4 term is diagonal. Okay. But O cube term is not. Okay. Similarly, fourth order commutator, I have done it with H right now, but effectively what we really want is a term which is proportional to kind of MC squared piece. Okay. And anyway, but if you do this commutator, you get a term which is beta O to the 4, which is again diagonal. Okay. These commutators are simple. This is just S dot, which is going to be O dot because O contains pi. P is of course not a time, is an operator which is time independent, but A, you can take time derivative of it. Okay. Similarly, S dot commutator is a commutator of O with O dot. Okay, so that is another piece that you need to keep. So if you put all these terms together, there are some pieces which are kind of common. You can see that there is a O cube piece sitting around here, and there is a O cube piece sitting around here. There is a O squared here and a O squared there. There is a O to the 4 here and O to the 4 there, and so on. So you need to collect these terms, and you find that after collecting all these terms, you get your Hamiltonian in this particular form. Okay. So I have written them in a specific fashion. You can see that it is proportional to beta times MC squared plus O squared, which is diagonal, upon 2MC squared minus O to the 4 upon 8M squared C to the 4, which is again diagonal. So this entire piece is diagonal. Okay, plus E phi, which is also diagonal. Okay, so remember when we started off, we had only beta MC squared and E phi to be diagonal, but now you have beta MC squared plus E phi, which are of course still diagonal, and two more terms which are proportional to O squared and O to the 4, which are diagonal. Okay, fine. Then there is one more term which is diagonal, and that is sitting here, which is minus 1 over 8M squared C to the 4 times double commutator of O with E phi. Okay, so what we have found is that we have converted at least 3 more terms in the Hamiltonian which are diagonal. Okay, and then there are a bunch of terms which are not diagonal. Okay, so here's a term which is proportional to alpha. This is proportional to alpha cube. That means again proportional to alpha. This is a proportional to alpha, and hold on, this should have been comma again. And this is a term which needs to be kind of looked at carefully. Okay, we will kind of interpret that in a correct fashion. Okay, fine. So yeah, good. So as I said, that all the terms involving even powers of O, but not involving the derivative of O, are all diagonalized. Okay, so which are precisely the first parenthesis, E times phi term, and first term in the second row. Okay, which are all diagonalized. Okay, then we have like bunch of terms sitting around here which are still not diagonalized. Okay, so what we'll do is that that we will kind of find out another transformation. Remember, this is the transformation which we call S1. Okay, and I said that like the total transformation S is going to be S1 plus S2 plus S3 kind of stuff. It's kind of infinite sequence really. And so what we'll do is we'll try to find out a new transformation which will take care of the terms which are off diagonally in this Hamiltonian. Okay. So any questions at this point?
So O dot is not diagonalized because we have different terms of like different coefficients of alpha in O and O dot, right?
Uh, Sorry, I couldn't hear properly.
So this last term O dot,
O dot, yeah.
yeah, that is not diagonalized because we have different terms of alpha, different coefficients of alpha in O and O dot.
Yeah,
Okay.
exactly. Yeah.
Yeah.
So we will see how that needs to be taken care of. But yeah, precisely that is the reason. Okay, fine. So what we'll do now is that we will follow the same intuition that we followed in the first step. That is that look at the diagonal piece and say that like, okay, this is a piece that is doing a good job. We don't want to touch that fellow. Look at the off diagonal piece and claim that this off diagonal piece multiplied by beta, okay, is the new transformation. Okay, it looks quite ugly, but that's how you would do it. Okay, so here's the transformation. Okay, so S2 is a transformation where you multiply by minus I beta upon 2mc squared. Remember that was a factor sitting around. Maybe I can roll this stuff down. Oops, quite some distance away, right? Minus I beta upon 2mc squared, that is the same factor. But now this operator is the off diagonal piece sitting around in this H prime. Okay, besides this commutator, we are writing down a term which is this, and this. Okay, precisely those three pieces. Okay, and let's call that this entire stuff inside the parenthesis as O prime. Okay, and carry out the same computation. Okay.
What about the last term, the O comma O dot?
Yeah, so that term also has to be taken care of. So what we will do is actually we'll do it at the third step. When we do S3, then we will kind of take care of that term. But uh, uh, I mean, the reason why we do it in different steps is because these are the terms involves the derivative of O, and that term is the commutator of O with the derivative of O, which is like a higher order piece. Okay, so that is the reason why we don't do it at this level. Okay, but of course, you don't have to do it in those steps. You could have just done it right at this step by adding a commutator of O with O dot and done the calculation. Okay, so basically what I'm trying to say is that this term is order 1 over mc squared, whereas this term is order 1 over m squared c to the 4. Okay, so that is the reason why it's kind of something we don't look at right now. Okay, fine. So what we do is that like okay, so this piece is the off diagonal piece, but that commutes with the identity matrix. This entire piece is proportional to identity matrix. Okay, and therefore we don't need to worry about that part. Okay, now it doesn't look like it is always proportional to identity matrix because there's a beta matrix sitting around there, but that fact that there's a beta matrix sitting around is taken care of by putting a beta term inside this transformation. Okay, so this entire object actually commutes with the diagonal part of the Hamiltonian. Okay, so only thing that we need to do is to uh, look at the piece which is off diagonal and its commutator with this piece. Okay, so it's like commutator of this operator with itself in some sense. Okay, fine. So so what one could do is to basically compute this commutator again in systematic fashion. Okay, and whatever are the off diagonal pieces that would survive, one can do another transformation S3 and try to push those off diagonal terms to even higher order. Okay, now what we will do is we will not do all that. Okay, we will just look at the terms that are kind of relevant for us. Okay, and let go of the remaining terms. Okay, so remember these are the terms that we had looked at. Okay, so 1, 2, 3, and I mean, sorry, 1, 2, and 3. These are already diagonal terms, and then out of all these pieces, we basically write down one additional term. Okay, and that is the term which is this. Okay, the commutator of O with itself. Okay, just a second. I need to check whether I have a typo in this. Yeah. Yeah. Sorry. So I really have the commutator of O with O dot, because otherwise this wouldn't make sense, right? I mean, this is just would have vanished. Okay, so this is O dot really disaster. Okay, fine. So, but coming back to this, what we'll do is that we'll look at these expressions, okay, and try to simplify these expressions and give meaning to each one of these terms. Okay. So let's start with the first new term, which is, remember, beta MC squared and E5 were the original diagonal terms. This is the first diagonalized term. So let's look at that term first. Okay. So remember, O was C times alpha dot P minus E by C times A. Okay. So O square is going to be the square of that quantity. Okay. So so if you do that, then you have kind of two terms coming out here. Okay. Remember, the alpha matrices have the product property that alpha I alpha j is equal to delta ij plus I epsilon ijk times sigma k. Remember, if you how much back I may have to go, but I don't know whether you remember this relation. Alpha matrices were off-diagonal sigma matrices, and sigma matrices have the product relation sigma I sigma j is equal to delta ij plus I epsilon ijk sigma k. Okay, and because of that relation, alpha matrices satisfy a similar relation that alpha I alpha j is equal to delta ij plus I times epsilon ijk sigma k, where sigma k is a product of two alpha matrices. Okay, so what we are going to do here is that we expand this term. Remember, this is a scalar quantity. So when you square it, you actually have double product of the scalar quantity. So you write down that as alpha I pi I times alpha j pi j. So in that product, you have alpha I alpha j. When I is equal to j, you get this term, okay, which is pi I times pi I, which is this piece. But when alpha I is not equal to alpha j, then you get epsilon ijk times the sigma k, and that epsilon ijk times sigma k term contains is proportional to this. Okay, so this is the sigma k operator, and the epsilon ijk piece contains pi j times pi k, or pi I times pi j. Okay, fine. So, but pi I times pi j with I not equal to j, anti-symmetrized, because there's epsilon ijk sitting around, okay, tells you that pi is acting on aj and pj is acting on ai. But pi acting on aj minus pj acting on ai is curl of a. Okay, and curl of a gives you the magnetic field term. Okay, so you get epsilon ijk times sigma k times del I of aj minus del j of ai, which gives you this magnetic field in the k direction. So sigma k dot times b, that is a term which comes out of the product of two alpha matrices. Okay. So of course, this is a piece that we kind of know. This is exactly what we would have done in Schrodinger equation, that when you have a charged particle coupled to electromagnetic field, then p squared by 2m would be replaced by, so there's a c squared getting cancelled here. So you have a p squared by 2m replaced by p minus e by c a whole squared by 2m. And that is precisely this piece. Okay, this is a new piece which you would have put in Schrodinger equation by hand, but this is a piece which naturally comes out of the Dirac equation, which is the coupling of the spin with the magnetic field. Okay, so this is what is called the S dot B coupling. Okay, fine. Can you hear me? Hello?
Yeah.
Yeah,
Oh,
now
okay. And there's some disturbance in between?
Yeah, there was.
Oh, okay. The computer tells me that the connection is unstable only after it was unstable. That is kind of useless information. Okay, anyway, so coming back to this stuff, so we want to look at the next term, okay, and next term is a commutator. So this is supposed to be O dot, and so it's a commutator of O with commutator of O with E phi and with O dot. Okay, so I first compute this piece, and then we'll compute this commutator with O. Okay, so here is the expression. 1 over 8 m squared c to the 4, which is a piece sitting around for both of them. Okay, and then you get commutator of O with E phi plus I times O dot. Okay, so okay, good. So when you look at this expression, then you notice that O is P minus E by CA, and of course A is going to commute with phi. Okay, there is no differential operator or nothing like that, but P is not going to commute with phi. Okay, so therefore what you get is alpha dotted with P acting on phi, which is the gradient of the electrostatic potential. So that is a piece which comes out of this term. Okay, whereas I times O dot, in this case alpha and P are kind of time independent quantities, but A is not. So this acts on the A and it gives you alpha dot A dot. Okay, so this is a dot product of alpha matrix with the time derivative of the vector potential. But now you see that if you pull minus I times alpha out, or maybe I times alpha out, then you get minus gradient of phi minus time derivative of the vector potential, which is precisely the electric field. Okay, so here's a new term that you get from this commutator. Okay, so this is kind of pretty similar to sigma dot B, which is now alpha dot E, where E is the electric field. Okay, fine. So now what we want to do is not use this term really, because this is only part of the computation. This term, we want to actually compute commutator of this term with O. Okay, so let's take this result, alpha dot E. Okay, and now compute commutator of O with this operator. So all this IE h bar upon 8 m squared c cube and all are just going to sit outside. O also has another factor of C, which is also going to sit outside. And what we really want to compute is a quantity like this. Okay, alpha dot P is alpha dot E, this commutator. Okay, again the same rule. You know, both of them are scalar quantities. So when you write down their product, then you want to ask what happens with alpha products of two alphas. Okay, if those two alphas carry the same index. Okay.
Sir,
Yes. Yes.
sort of cut right now.
Hello. Can you hear me now?
Yeah.
Hello. Sorry about this.
Hello, can you hear me?
Yes, I can hear you.
Yeah.
I'm sorry for this. Network has decided to kind of play games again. Can you hear me now?
Yeah.
Okay. So let me step back again. I hope you were with me when I said that this. Hello. Hello.
Yeah.
Yeah. Okay. Because it again started showing me internet is unstable, but I think it tells me only after it has been unstable. Okay, so I suppose you were with me when we computed this commutator and O dot piece and said that that was proportional to alpha dot E. Is that
Yeah, we
correct?
could do that. Yeah.
Okay, good. So maybe we can start from here. And what we want is not this expression, but the commutator of this with O. Okay, so let's do that. So O is again alpha dot pi, but in that commutator of A with this expression is kind of 0. So therefore, what is relevant is really operator P. So therefore, we have alpha dot P commutator with alpha dot E. Okay. But before I do that, I think Sukalpa had some question, or maybe it was related to that same thing that he couldn't hear or something, internet problem or something.
No, Aman was just pointing that your voice had gotten cut at that time.
Okay, thank you. So I was not sure, like, okay. So let's get back to this one. So again, we are in the same situation. We have alpha dot P with alpha dot E product. Okay, and if both the alphas are same, then you get alpha, so alpha I pi alpha j ej. If I is equal to j, then you get delta ij, and the P acting on E will give you del dot E piece. Okay, so that is this piece. But if alpha I, alpha j, I and j are not same, then you get epsilon ij k sigma k, and then epsilon ij k with pi ej gives you a cross product del cross E. Okay, because epsilon ij k pi ej. Okay, but that cross product, I should have really put a bracket here because sigma is dotted with this entire cross product and not with del. Okay, so you get a term like this. Okay, fine. So in addition, of course, you have one more term, and that is that, remember, when P acts on E, you get del cross E, but when P goes across, okay, then you get E cross P, okay, which is this term. Okay, so this term, which is the term in the Hamiltonian, has three pieces. One piece is a del dot E piece, the other piece is sigma dot del cross E piece, okay, and the third is sigma dotted with E cross P piece. Okay, so these are the three pieces which come out of this expression. Okay, the last term that we want to look at is this O to the 4 term, excuse me, and this O to the 4 term is just P to the 4 term. Okay, P to the 4 upon 8 m cube c squared. Okay.
So
Yes.
that E cross P will it not cancel when we, like, because it's a commutator, there's a minus alpha dot E alpha dot P acting on state.
No. Yeah, it would have cancelled if alpha factors were not there. Okay. Even when you have alpha I, alpha j piece, okay.
Yeah.
Then what happens is that you have a term which is epsilon ijk pi ej. Okay, and then what happens is either pi acts on this or it doesn't act on that. When it goes across, then because of epsilon ijk, that term survives actually, and you get this term. Those two terms get added actually. That is why these terms are 8 m squared c to the 4, whereas this is 4 m squared c squared. Okay,
All right.
You get twice as much, in fact. Okay. We will see this similar thing happening later on also when we start manipulating terms, which is, see, we have to manipulate this term also, P minus E by C A whole squared. And in this expression also, when P could act on A or P could just go across, and you will find that that term also adds actually. Okay. You would think that like commutator would not have done that, but because this alpha matrix relationship which gives you epsilon, the commutator gives you a minus sign and epsilon also gives you a minus sign, and they add actually.
Also, dimensionally, it should be C square everywhere instead of C4.
Is that? Yeah, you may be right actually. Why am I writing 6 to 4? Yeah, absolutely no reason to write c to the 4. It has to be c squared actually. All of them have to have same m squared c squared term. I will correct it. Thanks for pointing out. I would, it would have just gone unnoticed for me. Okay, good. Yeah, I'll correct it.
Yeah.
Okay, so what we have found at the end of this computation is that our Hamiltonian looks like this. Okay, we have this rest mass piece, then this is a Schrodinger kinetic term kind of piece. This is the relativistic correction piece. This is the Coulomb interaction piece. This is a coupling of spin with magnetic field. This is a coupling of spin with curl of electric field. Okay, and this is a new term. We will see what happens with this term. And this is a del dot E piece. Okay, each term has some interpretation. Okay, so this is the one which sigma dot B is called magnetic dipole interaction. Del dot E is the term which is called the Darwin term. Okay, apparently, I don't know how much of that is true, but apparently Dirac was so confident of this equation that he didn't even want to solve the hydrogen atom problem using his Hamiltonian. He just told that it will work out right. But some people said that like he was actually worried that what if the spectrum doesn't work out correctly. So he did not compute it. Darwin computed that, and Darwin figured out that in the non-relativistic limit you have this term which Schrodinger equation did not have, and that's why that term has a name Darwin term. And he's the first one to officially in the sense in print, he's the one who has actually solved the hydrogen atom problem using Dirac equation. On the other hand, the Cambridge University people said that Dirac in fact knew the entire answer and he didn't even think that it was worth publishing. So anyway, that's supposed to be the history, or not history, but the gossip about history. Okay, so coming back to this, that in this case, suppose you look at the electrostatic situation. Okay, then if you are looking at electrostatic situation, then you will get the curl of E to be 0. Okay, and therefore you could kind of ignore this term of coupling of spin with the curl of E. Okay, so in a non-relativistic limit, we can kind of say that like for electrostatic problem, we could happily set this to 0. Okay, but this term would survive and we will kind of massage it a bit. Okay, so here's a kind of manipulation that, yeah. Okay, so this is yeah. Sorry, this is a repetition. I didn't want this term here. Okay. Just hold on. Okay, I could have corrected other pieces also, but like let's get this corrected first because I don't want it here. Okay, so the point that I am getting at is that if you're in the electrostatic case, then your electric field is just minus the gradient of the Coulomb potential. Okay, and there is no minus del A by del T piece. Okay, remember this is a piece that we used. Let me just step back a little. This A dot piece minus A dot piece was also part of the electric field, but if you're in the electrostatic case, you wouldn't have a term like that because there is nothing time dependent in electrostatics. Okay, and if that is the case, then your electric field should be just written as minus the gradient of the Coulomb potential. So you write that expression times, of course, the gradient is a vector, so it is along R times crossed with P. Okay, so here is a term. Okay, R cross P. Okay, but R cross P is something we know, that is angular momentum. Okay, So what we can do is we can pull out 1 over r del phi by del r out, and you get sigma dotted with the orbital angular momentum. So this is a spin orbit coupling term. Okay, and this spin orbit coupling term is proportional to the gradient of the Coulomb potential. Okay, so therefore, in the electrostatic case, we can ignore del cross E term, but we keep this E cross P term, which actually gives you a spin orbit coupling. Okay, fine. The Darwin term del dot E basically tells you that you cannot localize the electrostatic, you cannot localize the relativistic particle in a region smaller than its Compton wavelength. Okay, so that is the statement of the Darwin term. We will use it when we do atomic physics problems without actually directly using the Darwin term, but there are kind of indirect way of utilizing this result. Okay, so Darwin's observation was that, like, because of this term, what happens to the particle is that it actually sees a smeared potential, and he tries to kind of show how del dot E term correctly captures this effect that the particle sees. Okay, so we can ignore it. Yes.
In the hydrogen atom case, this is simply delta function. This Darwin term.
Darwin term is a delta function. Yes, that's what we will do, in fact. Okay. So in the non-relativistic case, we'll just replace this quantity by a delta function. Okay. So that's why I said, like, we will not use in a del dot E form, but we'll use the delta function form. You're right. Okay.
Yeah.
Okay. So so what we'll do is we'll basically take these pieces and try to kind of use these pieces when we study atomic physics problems. And of course, first we will solve the exactly solvable part of this problem, which is like Schrodinger equation. We are of course going to forget about this MC squared piece. We'll look at this part and the Coulomb potential, and then we'll kind of systematically add various other terms, and of course we'll manipulate those terms to kind of bring it into a form in which we can kind of study them perturbatively. Okay, so that is the approach that we are going to take. Okay, so any questions at this point? Okay, so of course, as I said, a lot of this computation is very technical. I have not given all the details, but it will be home assignment. Some of the computations will be home assignment, not all. You can look at various books on relativistic quantum mechanics where these things are computed. The best kind of computation is in Bjorken and Drell relativistic quantum mechanics. And I may be wrong, but I believe that most of the other relativistic quantum mechanics books basically just copy the computation done by Bjorken and Drell, with no offense meant. I mean, various other things they have done explicitly and differently, but I think Foldy-Woutersen is best is in Bjorken and Drell. Okay. In fact, my derivation is also, well, not derivation, my notes are also from Bjorken and Drell only.
Okay. Which book, sir?
Bjorken and Drell. BJORKEN. Drell. D-R-E-L-L.
Would you spell it again from the start?
B for ball, JORKEN. Okay.
Okay.
And Drell, DRELL. Okay.
Yeah. Okay.
Bjorken, I mean, there was a tennis player called Bjorn Borg. Remember? The same BJO. That is, Bjorken is similarly spelled. Okay, Swedish name. Okay. They have two books actually. One book is called Relativistic Quantum Mechanics. The other one is called Relativistic Quantum Fields. Okay. So this is there in Relativistic Quantum Mechanics, which discusses Dirac equation in reasonably good detail. Okay.
So,
Yes.
if del dot E is a delta function in hydrogen atom case, this
Yeah.
delta function would instead try to localize the electron around the center, right?
No, no,
Because
no, no.
there's a minus sign with delta function.
Yeah. So what it tells you is that like this delta function is sitting at the origin, okay, and that is the reason why any uh, electron wave function which is non-vanishing at the origin is the only one which will see this term. Okay.
Yeah.
Remember, most of the electron wave functions vanish at origin. Only electron wave function which does not vanish is the S wave. Okay. So this effect is seen only by S wave function, and all other wave functions do not see this effect. Okay. So that is the kind of effect you will see. Is it okay?
Okay.
Yeah.
Okay.
So yeah, but this is a delta function potential. You see, it's not like it is not trying to kind of. So delta function doesn't localize the wave function the way. Yeah, I understand what you're saying. Schrodinger equation in
Yeah,
quantum mechanics.
relating it to one dimension delta function potential.
Yes, yeah. But it's not like that. It's like the problem is already solved for the Hamiltonian important parts of the Hamiltonian. It's a subleading piece, and you want to ask, given the basis of states, okay, written in terms of YLMs and the Legare polynomial, in that basis, this perturbation affects which set of states, and this perturbation affects only those set of states which are non-vanishing at the point at which this potential is non-vanishing. Okay, that is how it is computed. Okay. Fine.
So
let's,
earlier when
yeah,
we were solving it, the entire problem,
yeah.
why didn't this term appear there? Like
Which term?
when you're trying to write the spinor in terms of f and g, two different
Yeah,
functions,
yeah,
and try to solve exactly the differential equation,
yeah.
we practically solved it, right, entirely.
Yes, yeah. So it is there even in this problem. It is there. You just have to kind of dig it out correctly. Okay. It does affect some S wave function. I know what you're saying. You're saying that when we are doing this computation, where is that expression? No.
Yeah.
Yeah, it is there. You just have to dig it out. This thing. I glossed over it clearly. Okay. But Darwin term does affect the lowest J values, in fact.
Okay.
It's there. I mean, like, in fact, it was mentioned this thing that if you have like lowest J value, then you have only J is equal to half, and then there is a other correction coming from the spin. There's only one way you can get J equals half, and not two different ways of getting it. And that corresponds to L is equal to 0 term contributing in a particular fashion. Okay.
Yeah.
If you trace it back, it is related to the Darwin term. Yeah, but it is possible to see it even in the full problem. Okay, so let's start atomic physics now. Okay, so much for actually doing the atomic physics problem. We are going to start off with the hydrogen atom thing, but we are not going to solve this problem again because we have done it just too many times already. Once in QM1 course and twice in this course, once using Klein-Gordon equation and once using Dirac equation. So we are not going to try solving this, but we know the following thing about the problem, that this spectrum has degeneracy, and it has a 2 times 2j plus 1 degeneracy when j is less than n minus 3 by 2. Okay. Uh, Whereas when j takes highest value, which is n minus half, then it has only 2j plus 1 degeneracy. Okay. So that is because here you have both parities contributing, but the highest state has only one L value contributing. Okay. So that is the reason why it is only half the degeneracy for that state. Okay, fine. Now, all these degeneracies that we talked about was when we solved the Schrodinger equation with only the Coulomb potential piece. Okay, but this degeneracy gets kind of lifted by various other corrections that we have already listed. Okay, and in particular, there is one important correction which comes through quantum electrodynamics. This is a quantum field theoretic correction called the Lamb shift. And it is this Lamb shift which tells you that the 2s half state and 2p half state, which should have been degenerate according to this formula, actually they are not degenerate. And in fact, 2s half state has energy higher than 2p half state. Okay. Now, this is one computation that we will not do in our course, but this is one computation that you will do in quantum field theory course, or you may have to do that as a home assignment. I don't know what is the plan, but this is one of the greatest triumphs of the quantum electrodynamics, that it correctly reproduces this gap between the 2s1 and 2s half state. Okay. Now, this gap is in these two states which should have been degenerate had the non-electric hydrogen atom problem was the complete story. Okay, this gap is quite small, in fact, but nevertheless, it was observed experimentally first and explained by theoretical calculation later. Okay.
2s half has more energy than 2p half.
Yes. Yeah. Yeah.
Then
2s half.
why do we fill electrons in 2s first, like in periodic table or in elements? Isn't the rule that we follow that we'll fill the lowest shells first? Like first we start with
Yes.
1s, then 2s, 2p, 3s, 3p, 4s,
Yes.
3d, 4p, and all.
Yeah. Yeah. So you would have filled up 2s first, but you do find this gap in it, and but this gap is very small actually, some thousand. Yeah, I don't know what it is. It's some 1 gigahertz or something like that is the gap, and yeah, good question. I don't know the answer to this right now, but I think there are some other corrections which kind of shift these states anyway, namely, finite size of the nucleus and finite spin of the nucleus terms. But if you just look at this calculation, this answer is in this order, if I am correct.
Also, maybe multi-electrons won't, like when we are filling
Yeah, this
elements,
is,
we
of
have
course, you are
multiple
solving a
electrons.
single electron problem.
Yeah.
Here you are solving only single electron problem. When you are trying to fill it up, of course, there is a electron repulsion factors also you have to take care of, but that is the atomic physics problem. Okay, this is a single electron problem actually, and this result is actually correct, that you get 2s half having higher energy than 2p half. This is a Lamb shift computation.
Okay.
Yeah, I'll get back to you. I don't know. I just can't think on my feet right now. Okay. Fine. So what we will do now is that we will start with this as an input, that this is a degeneracy. But this degeneracy is, and this spectrum has been computed by assuming two things. One thing is that we said that there is a potential, excuse me, there's a potential generated by some charged object. Okay. And we assumed that that charged object is not affected by the motion of electron. Okay. So electron is moving in that Coulomb potential. Okay. And the Coulomb potential has no back reaction on it. Okay. That statement corresponds to the assumption that the object which created this Coulomb potential is infinitely heavy. Now that is not true, because nucleus has finite mass, and therefore you have to take finite mass effect of the nucleus into account. Okay. Now this is something we have done in some sense when we tried to solve the Schrodinger equation. We said that, like, instead of working with electron mass, we will be working with reduced mass. Okay. that is a kind of reduced mass is essentially the effect of accommodating the finite uh, accommodating the finiteness of the mass of the nucleus. Okay, so that is one problem which in Dirac equation you cannot do by hand. Okay, uh, there is no natural way of kind of introducing finite mass of the nucleus in the hydrogen atom problem in Dirac equation. Okay, so that is one thing that we will deal with. The second thing that we have to deal with is that nucleus itself may have a spin. Okay, we so far assume that nucleus is just a charged object and which produces a Coulomb potential, but it may not have any effect on, say, electron spin or electron orbital angular momentum and so on. Okay, and we will have to correct both those quantities. Okay, so uh, so what we'll do is that we'll kind of look at the nucleus in a little more detail. Okay, and ask what are the terms that it would contribute to the Schrodinger equation besides whatever which has come from the Dirac equation. Okay, the terms which come from Dirac equation are just listed, right? P to the 4 term and stuff like that. Okay, this entire list. But besides that, we'll have to ask what is the contribution coming from the nucleus. Okay, so this is like finite spin and finite size of the nucleus. Okay, so of course, nucleus itself is a complicated object, consisting of various protons and neutrons interacting through strong interactions. But that is not our concern at all, because the electron is like far too away from the nucleus. Nucleus is of the size of 10 to the minus 15 centimeters, whereas the electron orbit is of the order of 10 to the minus 10 centimeters. Okay, so it's like a 5 order of magnitude distance between size of the nucleus versus the size of the orbit of the electron. So in that sense, electron need not worry about how strongly or how complicated is the interaction between protons and neutrons. Okay, but so therefore we can completely ignore that piece. Okay, also because it is 5 orders of magnitude distance between the size of the nucleus versus the size of the orbit of the electron, the energy scales involved for the electronic problem or atomic physics problem is much lower than the energy scale involved in nuclear physics problem. Okay, so therefore we need not worry about detailed structure of the nucleus and what Hamiltonian which governs the dynamics of the nucleons inside the nucleus is not a part of the problem that atomic physicists would worry about. Okay, but nevertheless we need to worry about some other things. Okay, that nucleus, because it has strongly interacting particle and strong interaction preserves angular momentum. Okay, therefore the nuclear Hamiltonian must be rotationally invariant. Okay, now remember that the fact that nuclear Hamiltonian is rotationally invariant does not necessarily mean that nucleus therefore is spherically symmetric. That is not true. Okay, in fact, what happens is that, like, if you have a Hamiltonian which has certain spherical symmetry kind of stuff, for example, say in hydrogen atom you have a spherical symmetry for the Hamiltonian, your wave functions are written in terms of angular momentum eigenstates. Okay, some wave functions are spherically symmetric, but some wave functions are not. Okay, so therefore nuclear Hamiltonian is rotationally invariant does not mean that nuclear states are necessarily rotationally invariant. In fact, they are classified by the nuclear angular momentum. Okay, and we will call that nuclear angular momentum I. Okay, now this nuclear angular momentum I has a property that it commutes with the nuclear Hamiltonian. Okay, that is a statement that Hn is rotationally invariant. Okay, fine. But so therefore the nuclear angular momentum is a conserved quantity as far as the nuclear Hamiltonian is concerned, but nuclear angular momentum could be some object which could affect the electronic motion, because electron has a spin and electron has orbital angular momentum, and both these fellows could actually talk to nuclear angular momentum. So remember the way we did addition of angular momenta when we consider, say, L dot S coupling, which is a spin orbit coupling term that we have here also. Okay, a spin orbit kind of coupling. Where is it? This one. Okay, so so in that case, what we did was that like we added the angular momentum, we wrote down a spin J, which was L plus S, and then interpreted L dot S in terms of J, L, and S. Like that, if you have nuclear spin, then we may have to kind of include nuclear spin along with the angular momentum, total angular momentum J of the electron, and write down I plus J and consider that as a complete angular momentum of the total system, and study the system including the nuclear angular momentum, okay, which is what we'll have to do, okay. But this quantity is invariant as far as the nuclear Hamiltonian is concerned, okay. Now since it's an angular momentum, it of course satisfies angular momentum algebra. So Ij is equal to I times epsilon ijk ik, okay, fine. Now remember that nuclear angular momentum is written like, if you want to write down nuclear angular momentum in terms of r cross p kind of expression, then I would be written as r cross p, but that r is a coordinate for the nucleus, and that p is the momentum of that nucleus, okay. So I is written as r cross p, but that r and that p is the coordinate and momentum of the nucleus, whereas L, which is r cross p for electron, is written as r, which is the coordinate of the electron, and p is the momentum of the electron, okay. So therefore, even if both these terms are written as r cross p, we are talking about different coordinates and different momenta of the particles, and therefore they commute with each other, okay. So electronic coordinates and nuclear coordinates actually have nothing to do with each other. So p of electron commutes with r of nucleus, actually, okay. They don't talk to each other because they act on totally different Hilbert spaces, okay. So similarly, Ik commutes with the electron spin also, okay. So in that sense, they are independently conserved quantities, okay, fine. Now given that I is conserved, it commutes with the nuclear Hamiltonian, we should be able to write down nuclear states as eigenstates of I squared and Iz, exactly the way when orbital angular momentum was conserved, the states are written in terms of L squared and Lz. So in this case, you have terms written in terms of I squared and Iz, okay. Now, although one can try to solve that entire spectrum for nuclear physics problem, that is not our concern, because we will be mostly interested in the nuclear ground state, okay. And the reason why we are interested in nuclear ground state is because, as I mentioned, that the energy scales involved in nuclear problem is much higher than the energy scales involved in atomic problem. For example, just to give one example, that if you look at, say, deuteron problem, that it's a problem of one proton and one neutron, and if you are studying that nucleus, then the ground state energy of that deuteron problem is 2.2 mega electron volts, 2.2 MeV, okay. That is the binding energy of that system, okay. So even for a problem as simple as two nucleon problem, the energies are of the order of million electron volts, okay. On the other hand, if you look at atomic physics problem, okay, then if you kind of consider reasonable value of Z, Z of the order of 20, 30 or so, the ground state energy is of the order of few kilo electron volts only, okay. So even with so many nucleons, Z is equal to 30 is like nucleons of the order of 60 to 65 nucleons. Even with 65 nucleons, the atomic physics problem is of the order of a few kilo electron volts. Whereas with 65 nucleons, the spectrum of the nuclear physics problem would be of the order of hundreds of MeVs. Okay, so therefore, if you are trying to study spectrum in atomic physics, even if you go from ground state to very large excited state, the total change in the energy would be of the order of maybe 100 kilo electron volts compared to, say, 100 mega electron volt energy scale between nearest states in the nuclear problem. Okay, so therefore, for entire spectrum of atomic physics, you can happily assume that nuclear state is the ground state. Okay, so what we are interested in is just looking at the ground state of the nucleus. Okay, so that is the same statement that I have written here, that the energy scales involved in atomic physics are much lower than those of nuclear physics. Okay, so therefore, for all practical purposes, you can assume that the atomic energy scale, in that energy scale, the nucleus is in its ground state. Okay, now even if you are assuming that the nucleus is in its ground state, that does not mean that it would necessarily be in the zero angular momentum state. Okay, it may be in the ground state of the Hamiltonian, but it may have non-zero angular momentum. Okay, so that means that the ground state of the nucleus would have I squared acting on it, giving I into I plus 1, and Iz acting on it gives you Mi as the eigenvalues. Okay, and these are the quantities which would be important for us in the atomic physics problem. Okay, is it making sense?
So is that L or I?
Yeah, I'm sorry. I also noticed this stuff, but it is I. It's terrible. I don't know what to do actually. I noticed it while typing also. Okay, I'll figure out a solution to this. I'll have to do something. It is really ugly. Yeah, sorry for this. I'll find out a solution. But let's continue with this right now. By the time we have next lecture, I would have hopefully cured it. Okay, so coming back to this thing, the rotational invariance of the nuclear physics problem would tell you that the ground state, if it has eigenvalue to be, capital I, then it will have 2I plus 1 fold degeneracy. Okay, it's the same angular momentum computation. Any angular momentum value is 2L plus 1, 2J plus 1 kind of fold degenerate. Okay, so therefore, kind of we will have to take this degeneracy into account when we take nuclear spin into account when we solve the atomic physics problem. Okay. Now remember that, like, this I is a total angular momentum. Okay, we are not going to look at what happens to individual nucleons inside the nucleus. That's not our concern at all. Okay, so how you get this I value from so many protons and so many neutrons is not our concern at all. Okay, we will not really worry about that. That is a problem handed over to nuclear physicists. Let them figure that out. Okay, fine. So now we are going to combine this system. So you are looking at an electron nucleus combined system, and now it is represented by N. You see, this is a problem, right? Only kind of keen eyes can figure out that this line is kind of thinner than that line, but it's kind of so terrible. I'll have to figure out some better solution to this problem. Okay, so bear with me this time around this thing. So this is NLS equals half. Okay, JM. This is how the electronic state was written, and IMI is the way the nuclear state is written, and the total state would be written as a tensor product of these two states. And of course, they have 2 times 2j plus 1 times 2I plus 1 fold degeneracy when j is less than n minus 3 by 2, and this factor of 2 would be missing when j is equal to n by minus half. Okay. So yeah.
Typically, like when you are doing, let's say, something like addition of angular momentum, we have something like net J vector is J1 cross identity plus identity cross J2 sort of a thing. That we sort of do because at the end, the operator that we'll measure is the net angular momentum of the two things combined.
Yes.
and we cannot like diagonalize simultaneously the individual J12 and
Yes.
the net thing. So instead we just diagonalize or at least consider the net J, and that's why
Yeah,
we do this angular momentum addition.
that is
So
right.
here also, are we saying that at the end we'll calculate the net angular momentum of the atom itself and not of the electron or the nucleus separately?
Exactly, exactly. So we are going to write down a new angular momentum, which is J plus I, which we will call F, and write down in terms of F actually.
But like, can we not study them independently in the sense that just figure out what the angular momentum of the nucleus is?
No, because there are coupling terms. We will see all those coupling terms coming up. Okay.
Like I commutes with our Hamiltonian, right?
I commute with our Hamiltonian, yes.
And so does J.
Yes, yeah. But nevertheless, there are terms involving these guys, and we will take those terms into account. We'll see as we'll proceed. We'll see more and more terms will start kind of tumbling out. Okay, so here's a change that I made with L. Is this L kind of better than this I?
Yeah.
So I'll do that change at various places. Sorry for this. Yeah, so we will need this. We will see that all these terms are actually going to be part of the game. Okay. Any other question? Oh boy, it is like 4:30 already.
Yeah.
Oh, I didn't even notice this. Oh, sorry. Okay, so maybe I think I'll stop at this point. We'll pick up threads from this point on. Okay. Sorry, I got overexcited with this. I should have probably. But it's okay. I'm not overshot. But please, if you have any question, do let me know. Okay. I just want to say one thing, that this Foldy-Wuthausen stuff that I did, I went a bit too fast probably. At least that's what I feel. I mean, uh, in case you have any questions, I would be happy to kind of take it up again. I can kind of uh, I can scan and put handwritten notes up, but only those terms which are not going to be part of the home assignment. I'm sorry for that. Okay, but do let me know in case you kind of feel that like Foldy-Wuthausen went a bit too fast. Okay.
Sir, how far
Yes.
is this going to go? Like, you are supposed to teach till which part?
Yeah. So I think the thing is the following, that uh, I was supposed to teach this particular course till November 20th or so. Okay. And I don't see how I'm going to ever cover this stuff by November 20th. I mean, that is like, taking atomic physics course every day till November 20th, then I would probably just cover. To kind of to put it in short, I have uh, what I have done so far up to this Foldy-Wuthausen is kind of was supposed to be preamble to the course actually, and atomic physics uh, course has actually started today, and I have like 3 notebooks of atomic physics course. I'm sorry. So I don't see how it is going to end by November 20th, but I will probably take it till end of November, I think. You know,
And
Hello?
after that, like, I mean, I can stop the recording. Yeah,
Yeah.
after that, what is Pinaki sir supposed to teach? Like,